Hello and welcome back to Calculus. First, as always, I want to thank all the nice people that support this channel by liking and subscribing. In today's part 34, I want to talk about the Euler's method for solving differential equations. So far, since part 30, we began differential equations. We've looked at analytical ways to solve a differential equation. We began with separation of variables and then moved on to homogeneous differential equations, which required a v substitution. And finally, we did exact differential equations, where we had to multiply the entire thing by an integrating factor. However, there are also many differential equations that aren't solvable using analytical methods. Thus, we need a numerical method, and hence the Euler's method exists. It's used to approximate the solution given an initial condition. To begin with, I want you to consider a simple differential equation, which is given by dy over dx equals to y, where we have a given initial condition y of 0 equals to 1. Now, this can be solved using separation of variables. What we get is the natural log of y is equal to x. And of course, plus c in the end. However, the given initial condition just tells us that c is equal to 0. So that means that y is equal to e raised to the power of x. So let's visualize this on a graph. Here we have a graph of the function e raised to the power of x. Next, let's build a table with 3 columns, namely x, y, and dy dx. Now, since we're given an initial condition where y of 0 equals to 1, I can put that into the table. When x equals to 0, y is equal to 1. So then what is going to be dy over dx? Well, from the differential equation, we know that it's just 1, because dy dx is equal to the value of y. So we visualize this on a graph. At the point 0 and 1, the slope is about 1. However, instead of doing this at every single point, we know that the slope is constantly changing. But what if we assume that for now it is fixed until the next x value? On the graph, you can see we started with the x equals to 0, so technically the next x value that we can see is 1. This means that we take a step along the x-axis, so a change in x. For the sake of simplicity, let's say that this change is 1. So I can note to myself that delta x, or change in x, is equal to 1. So now that means we assume that throughout this step, the slope is going to be 1. Now, if initial x was 0 and we take a step equal to 1 unit, that means the next x value is going to be equal to 1. What I did is that I simply added 1, because that is my step. Now, what about the y value? If I originally had y is equal to 1, and the slope throughout this step is equal to 1, that means that a 1 unit increase in x denotes a 1 unit increase in y. So that means y now is going to be equal to 2. So what is dy dx? Well, from the differential equation, we know that it's equal to the value of y. So that means dy dx now is 2. So now on the graph, I have reached the point where x is equal to 1 and y is equal to 2. And now the slope has become 2, so just a little bit more steep. Now let's move on to the next x value. So if you are taking a step of 1 unit, the next x value is going to be 2. What's the y then? Well, originally I had y at 2, and now the slope is 2. So that means for every 1 unit increase in the x value, I have a 2 unit increase in the y value. So now y is going to be 4, and dy dx is also going to be 4. So now on the graph, I have reached the point where x equals to 2 and y equals to 4. Please keep in mind that throughout each step, we assume that its corresponding slope is constant. And finally, let's do one more. So the next x value is going to be 3. What about the y? Again, y in the previous point was at 4, and the slope is also 4. So that means for each 1 unit increase in the value of x, I have a 4 unit increase in the value of y. So now y is going to be 8, and their corresponding slope is also going to be 8. So now on the graph, we have reached a point where x equals to 3, and y is approximately 8. Now you might say that this isn't a very accurate approximation, and I would agree. However, we took a fairly large step of x for the sake of simplicity when calculating this by hand. If I were to decrease the steps of x down to perhaps 0.5, or I could also do it to 0.1, then the approximation would be much more accurate. However, a major limitation to the Euler's method is that at the steps of size 0.1, calculating by hand is already really difficult and very repetitive, and it is easy to guess in numbers who have lots of decimal digits. So most of the time, Euler's method is solved using computers who can make the x steps even smaller, perhaps 0.01 or 0.0001, which yields much more accurate answers. However, the point of the Euler's method is that you can find the value of the function without actually solving the differential equation. Here, however, I showcased a solvable differential equation so that we can visualize it on a graph and see what it looks like and compare the actual answer, in our case e to the power of x, to our approximation, the red line. So now that we know how it works, let's quickly take a look at the definition. So given a first order ordinary differential equation in the form of dy dx equals to a function of both x and y, we need to first select an initial point. Let's call it x0 and y0. Next, we need to use two recurrence formulas. One of them is x of n plus 1 is equal to xn plus h, where h is the step size. So from our example above, we had the initial condition x0, y0 at 0 and 1, and in order to get the next x value, we needed the previous x value added by the step size, which we denoted using delta x. For simplicity, we can just write it as the letter h. And the other recurrence formula is going to be used to find the next value of y. What we did before was simply use the previous y and add the step size multiplied by the derivative dy over dx. Using these two recurrence formulas, we can generate as many points as we want. And finally, we can just plot those points on a graph and they will create a smooth curve. So that's it for now. Next time, we will take a trip down memory lane and revise limits. However, we will be able to evaluate them with a more simple method that I will definitely show you. So I hope to see you there and have a nice day. Bye.